Okay, we're going to look at determining instantaneous rates of reaction from absorbance data. We're going to use SparkView, and I've got the data analysis written up in Google Sheets. You can do this in Excel just as well. Okay, so first, this is again just a login to Google Docs using the GNSPES account if you like. If you don't want to use this, again, use Microsoft. The advantage really with Google is that it's here, it's at home, and you really don't have to worry about saving the data. Alright, some things are clunky, you already saw the subscript problem, but for the most part, it seems to be able to do pretty much everything we need it to do. So, do as you like, but really, commands are all the same. Alright, you use whichever program you're more comfortable with. Okay, so I'm logged in here under the GNSPES profile. I'm going to go in, I'm going to find Google Sheets. I'm going to create a new sheet. Alright, I'm going to rename it for the experiment Lab 5. Okay, and I'm going to look at instantaneous rates of reaction. So I'm going to basically build the calibration curve that you built yesterday in the lab. So this is to convert an absorbance reading of potassium permanganate at 565 nanometers into a concentration of potassium permanganate. Now we're going to need this because we're going to use the colorimeters to monitor the progress of the reaction between potassium permanganate and oxalic acid. Alright, so I need to be able to interpret the graph. SparkView won't auto-adjust the graph for me. It won't, let's say, just output concentration versus time on the graph. It will give me an absorbance versus time graph, so I need a way to convert all the absorbance readings into concentration readings. So here's some sample absorbance data. All right, I'm going to graph this, create a trend line. All right, and then I'm going to later on use this. I'm going to use this data to convert my absorbance reading from rate of reaction from absorbance per second to moles per liter per second. Alright, so building a graph in Google Sheets is pretty much the same as it is in Excel. Just the menus are slightly different. I'm going to want to create a scatter plot. Alright, I'm going to title my chart appropriately. I'm going to title my axes appropriately. I'm going to set a trend line, make sure that it's a linear trend line. I'm going to get the equation for the line on the graph. Okay, I can set an R-squared value on it. All right, all the normal features from Excel. Okay, so I've got both my axes labeled. Now the default is no trend line, but we're just going to set one to linear. This data came out great. I'm going to show the R-squared value, just for no other reason than just to give me confidence in the fact that, hey, look, the data is a good fit. Okay, so there's a bunch of options there. You can make the line thicker, thinner, change the point size, its color, or anything like that. Okay, do as you like. That's user's choice. Alright, so now I'm going to insert the chart, keep it here just so I can move it. The work really here is done. The graph is, it's a cliche, but the picture's worth 1,000 words, showing me that, hey, look, it's a grid trend. I can actually use this to convert absorbance to concentration with a pretty high degree of confidence. Alright, these are the slope intercept commands. Alright, this is actually just giving me the slope and the intercept from this graph. But I'm putting it in a cell so that I can manipulate it later in a formula. You could just as easily type in the 1391 into cell B10 if you wanted. Alright, so now we're going to have a look at collecting the data for part 2 of this lab. So this is monitoring a reaction continuously. You're going to need to open SparkView, connect your sensor. Alright, you've seen this before. Alright, connect the sensor. All you were doing yesterday was recording the absorbance at 565 nanometers. Okay, so remember, zero the sensor with a blank, so put a cuvette full of water in it. All the absorbance should come out as 0 initially. Right, they'll start to vary slightly afterwards, but make sure that you zero it right away. Alright, so after this, what you're going to want to do, proceed to whichever solution that you're going to work with. Get a sample of it. Alright, you only need a few milliliters, because remember, you're only filling this cuvette 2/3 of the way. Alright, so now I'm going to click on green absorbance, just as was done on the screen there. I'm going to actually start monitoring. Okay, so this is, I've put in my sample of purple. Now I'm going to speed up the video here, and you're going to you can watch the reaction progress, both filmed and what should happen on your SparkView graph. So you can see the little dip in absorbance there from the initial value of 1.2. The 1.2 value, that was the reaction, or sorry, that was the permanganate before the reaction began happening. When I added the remaining third, when I filled the rest of the cuvette with the third full of volume, right, I diluted that solution a little bit more. So you can see the absorbance drop. Alright, the reaction then begins, you know, where it originally looked. That's sort of that second step down. Now, this reaction isn't being mixed, right? It's mixing itself, so as a result, the reaction doesn't really start right away. Alright, but as you can see, alright, both from the graph, alright, the absorbance is decreasing. You can see from the video, the solution clears a little bit more. Alright, so what we're actually going to say is we're going to find the greatest rate of change. So, you know, essentially, where is the steepest slope of this graph? Alright. Alright, so there we go. Reaction over. Alright, so you want to save the file at this point. Alright, I know the computers get kind of fussy. Save file as, save it wherever you like. Alright, I would encourage you to save it in your H drive somewhere, so that just in case something happens, you at least have the data. Alright, I've saved mine in my Topic 6 Kinetics folder. Alright, call it whatever you like, as long as you know what it is. Right, I'd encourage you to label it with the reaction conditions. Okay, save. Now you're going to need to find the tool for this. Alright, you can have a look around everywhere. Alright, you see the button on the bottom left there of the screen with a little picture of the graph. Brings up the tool menu. You can see the button that I have highlighted there in orange. Alright, is the slope function. Then go up to the top of the screen and just use the left and right keys there and move the cursor around until you see the greatest value of m. It'll give you both the x and y coordinates. Alright, but essentially what you're looking for the largest m value you can find. Now, largest meaning will be the largest absolute value. So the steepest slope from this reaction is going to be negative 0.003. Now the units here would be of the slope would be seconds to the minus 1. Okay, absorbance is unitless. Absorbance is your y-axis. Time is your x-axis. So no unit divided by seconds is seconds to the minus 1. The seconds to the minus 1 is important for the conversion that we're going to do later on. Alright, so now I'm going to use the calibration data to convert that slope into that steepest slope into a concentration. All right. So remember, my graph was related absorbance to concentration, so now I need to take that negative 0.003 seconds to the minus 1 measurement, and I need to convert that into moles per liter per second. Alright, so essentially what I'm going to do is I'm going to go back to my absorbance calibration graph, and I'm going to say, alright, if my absorbance value is negative 0.003, what concentration does that correspond to? Alright, and then what that's going to tell me is what is the greatest rate of change of concentration over time. Alright, so I'm going to put my 0.003 in this cell, and you can see on the screen, pause it if you need to. This is just the worked out solution in math type, what I'm actually doing, but I'm basically solving a y equals mx plus b equation for x. Right? Remember, on the calibration curve, concentration was your x variable. I'm supplying it the y variable of absorbance. Solve the equation. Alright, and I find that the negative 0.003 absorbances, if you will, per second corresponds to 6.5 times 10 to the negative 5 moles per liter per second. Alright, you can see I'll clean up the spreadsheet. You can put on your text wrapping, that sort of thing, so you can read it. You're not passing this in to me. This is just so that someday in the future, when you need to, you know how to clean up the Excel files. Alright, so the rate of reaction for 0.008 molar potassium permanganate with 1 molar oxalic acid is 6.45 times 10 to the negative 5 moles per liter per second. Alright, I'd like you to try this again, or you're going to do this again with 5 different temperatures of 0.008 molar oxalic acid. Alright, and you're also going to do it for 0.004 molar oxalic acid. Compare the trials. I'm going to provide you with the order of reaction with respect to oxalic acid, and you guys can determine both the rate constant and the activation energy.